Right now, in a sealed room inside an Intel fab, there is a machine the size of a small bus that costs $380 million. It is the single most expensive tool Intel has ever installed, and the company has bet its survival on it. Inside, lasers vaporize droplets of molten tin into plasma, just to carve features 8 nanometers wide onto silicon. It looks like the future. It might be a monument to the wrong bet. Because here is what almost nobody is telling you. The two largest chip makers on Earth, TSMC and Samsung, bought the same machine, looked at the math, and refused to put it on a production line. Intel did not. Intel went all in. This is the 14A node, and an Intel SEC filing has already admitted the company may shut down its entire foundry business if this gamble fails. We are going to expose why Intel bet everything on a tool its rivals will not touch, and the technology that could undercut the whole premise. For decades, making chips faster meant one thing: make the transistors smaller, and repeat every couple of years. But there is a problem buried in the method. You print a chip by shining light through a mask onto a silicon wafer, and light has a wavelength, a hard floor on how small a feature you can draw. Trying to print an 8 nanometer line with the wrong wavelength is like signing your name with a paint roller. The industry's answer was extreme ultraviolet light, EUV, at 13.5 nanometers, made by a single Dutch company, ASML. But Intel needed to go further, so it reached for the next generation, High-NA EUV. A wider optical aperture lets it print features down to approximately 8 nanometers in a single exposure. Intel says it can collapse certain critical manufacturing layers from around 40 process steps down to fewer than 10. But here is where the gamble shows its teeth. Each High-NA machine costs about $380 million, against roughly $235 million for current tools. These are staggering numbers, and cost is the sharp edge of the argument. Intel's own chief financial officer, David Zinsner, confirmed 14A will cost more to build than the node before it, specifically because of these machines. In December 2025, Intel completed acceptance testing on ASML's TWINSCAN ULXI 5200B, becoming the first major foundry to put High-NA on the path to high-volume manufacturing. That sounds like leadership, which raises an uncomfortable question. If this machine is so essential, why are the two biggest chip makers on the planet refusing to put it on a production line? The conventional wisdom is simple. Whoever adopts the newest tool first wins. So you would expect TSMC and Samsung to be racing Intel. They are not. Both companies bought High-NA machines from ASML. Then they locked them inside their research divisions and refused to commit them to a single production wafer. At the North American Technology Symposium, TSMC Senior Vice President Kevin Zhang stated plainly that the company will not use High-NA to manufacture its A14 node, its 1.4 nanometer class process arriving in 2028, the node that competes head-to-head with Intel's 14A. TSMC plans to wait until a later version, A14P, around 2029, and Chairman C.C. Wei was blunt about why. At the company's June 2026 shareholder meeting, he confirmed they had bought the tools for research and development, but the reason it is not in mass production is purely cost-related. Industry estimates suggest High-NA can raise production costs by up to 2.5 times versus conventional EUV. So TSMC made a calculation. Brute force EUV, even with more steps, is a known quantity. They can model it, predict its failures across millions of wafers a month. High-NA at that volume introduces unfamiliar risk. An unfamiliar risk at the scale TSMC operates on is not a setback, it is a catastrophe. Now connect that back to Intel. Intel is, for now, alone on the bleeding edge of high-volume High-NA. If the bet pays off, it leapfrogs everyone. But if 14A can't yield economically, Intel will have spent the most money on the most expensive tool in history, while its rivals quietly kept making chips the old way and never blinked. Intel even built a hedge into the node, offering customers a fallback to standard patterning. That tells you how much uncertainty is baked in. But the real threat to Intel's gamble isn't TSMC. It's a technology that sidesteps the fight over who has the better light entirely. Everything so far assumes one thing, that the way to print smaller features is to keep building better, more expensive light sources. But what if you could convince matter to draw them for you? That's the idea behind directed self-assembly, DSA. It relies on a strange class of molecules called block copolymers. Picture two chemically incompatible materials that repel each other, like oil and water, except they are chemically bonded together and cannot drift apart. So when you heat them, they organize themselves into perfectly regular, repeating patterns at exactly the scale chip-making needs, finer than 10 nanometers, formed spontaneously by thermodynamics. On their own, those patterns are random and useless. So here's the trick. You use ordinary EUV to print a rough guide template, not the finished pattern, just a fence. Then you apply the copolymer, heat it, and the molecules snap into place within that fence, like a self-solving puzzle. You used light to set up the playing field, then let molecular physics win the game, and the result can be sharper than the light that created it. This is not science fiction. The International Roadmap for Devices and Systems lists DSA as a candidate technique for the 3 to 5 nanometer range. Researchers at IMEC have run it on full 300mm production wafers at a 14 nanometer half pitch. Studies show DSA can act as pattern rectification, lowering the EUV dose required and cleaning up an imperfect template. Now hold that against Intel's bet. Intel's premise is that you need a $380 million machine to reach these dimensions. If chemistry can deliver comparable resolution at a fraction of the cost, the logic of going all in on high NA starts to wobble. The honest catch is, DSA is not ready to replace anything overnight. Its bottleneck is defect control and a near total lack of the design software the industry needs to use it at scale. It is a complement today, not a replacement, but that is exactly the kind of not ready yet that has rewritten this industry before. So what does this mean? Strip away the acronyms, and you have two opposing philosophies. On one side, total control, engineer every photon, spend whatever it takes, and force the pattern into existence. That is Intel's $380 million bet. On the other side, guided emergence, set the conditions and let matter resolve the finest details itself. If Intel's 14A delivers, the gamble looks like genius. But if chemistry-assisted patterning matures faster and cheaper than anyone expects, Intel may have bought the most expensive bridge ever built to a road its rivals simply walked around. You now understand something most headlines miss. This was never just Intel versus TSMC. It is brute force versus self-assembly. The history of chip making is the history of walls that were supposed to be permanent, and the people who found a way through anyway. Light is running out of road. Intel is betting on better light. Somewhere else, someone is teaching matter to build itself. The question is not whether 14A works. The question is whether Intel bet on the right kind of impossible. What do you think? Control or emergence? If you want to see which company is quietly positioning to win the next decade, watch this next.